Hey, welcome back. Here we are in Chapter 5. I'm going to add one extra thing in Chapter 5. I'm going to add bond energies, which is actually in 7.5, Section 7.5 in your book. I'm going to add it here because it just really does fit in very well with the material that we're going to cover. You'll see when we get there, I suppose. So the bad news is, yes, you have 7.5 on your test here as well. The good news is when you get to Chapter 7, well, that's one less thing you have to worry about. So you can look at it that way, I suppose. But what we're going to do is we're going to talk a little bit about thermochemistry here. I'm going to kind of change the order in which I present this as to how it's presented in your book. Because I just feel like I like the way I do it a little bit better than what they do. Sometimes when you deviate from the script, it just goes horribly, horribly wrong. So I guess we'll see how it goes. But same material, it just might be in a slightly different order. Hopefully you can make that transition somehow. All right, if you can, then please let me know. So let's talk a little bit about thermochemistry. When I say the word thermal, thermometer, what kind of springs to your mind? Well, heat. All right. You may have noticed that when you go into the laboratory and you added something to something else, you did a chemical reaction, you might have noticed the beaker felt like it was getting a little hotter. When you put that aluminum in that potassium hydroxide, you notice it kind of heated up. You thought, well, maybe that was just my imagination. Well, no, it wasn't your imagination. Sometimes when you do chemical reactions, things get hotter. Sometimes when you do chemical reactions, they actually get colder. All right, and it's not your imagination. So that's what Chapter 5 is all about. Why do some reactions give off heat? Is there any way I can predict how much heat would be given off? And so on and so on and so forth. All right? Well, before we get started, there are three basic concepts that you need to know to understand this chapter. So the first concept we want to talk about here is the concept of system versus surroundings. If you think about it, the entire universe can be divided into two places. Inside this room and outside this room. If you're not inside the room, you have to be outside the room. All right, well, everywhere in the universe can be divided into two places. You have the system and you have the surroundings. The system is what you're interested in. It's what you're studying. The surroundings is basically everything else. Technically the rest of the universe. System and surroundings is kind of arbitrary. Let's say, for example, I have a hot copper ball, and I'm going to throw it in the fountain out in front of the Student Union building over there. All right, so I throw my hot copper ball in the fountain. What happens to the temperature of the copper ball when I throw it in the fountain? Well, anytime I take something hot and put it in contact with something cold, heat transfers between the two from the hot to the cold until the temperature is the same. So if I throw my copper ball in the fountain, then it's going to cool off. It's going to lose heat. Okay, so maybe that's my system. Well, the question is, where did the heat go? Well, it went into the surroundings. So what are the surroundings? Well, there's water in the fountain, and that's going to absorb some of that heat. But some of that heat actually goes into heating up the fountain itself because it's made of metal and concrete. But the fountain is sitting on the sidewalk there on the ground, and so some of that heat goes into the ground and the earth. But at nighttime, when the sun's not shining, the earth radiates heat, and so some of that heat gets radiated into outer space. Make sense? When you're studying things, it's usually useful if you can narrow your surroundings down as much as possible. The more you can narrow your surroundings down, the easier your calculations are. So technically, if I want to know what happened to the heat in the copper ball, I would need to know how much heat went into the water, how much of that heat went into the fountain itself, how much of that heat went into the earth, and then what fraction of that was radiated into outer space. But really, in the grand scheme of things, where did most of the heat from that copper ball go? Well, it pretty much went into the water in the fountain. Does that make sense? All right, so if I can figure out how much heat the water in the fountain gained, I can call that my surroundings. The amount that gets radiated into outer space is so little that I can ignore it. And so what we're doing is we're simplifying our problem by narrowing our surroundings down as much as possible. And so when you design experiments, if you can narrow your surroundings down, you have less things that you have to take into account, which makes your calculation simpler. All right, but notice that system and surroundings is kind of arbitrary. You know, I could divide the entire universe into inside this room here and outside this room, but I could also say the entire universe is inside Texas and outside Texas, or on the planet Earth and not the planet Earth. Maybe I'm not interested in the copper ball. Maybe I care about the water in the fountain. So maybe the water in the fountain is my system. So what's affecting the temperature of the water in the fountain? Well, the copper ball. So the copper ball in that case would be my surroundings. So really, your system is whatever you want it to be. It really just kind of depends on what you want to study. And your surroundings is basically everything else. Make sense? Okay, second concept you need to know. You need to know something about a state property. A state property is a property that is path independent. In other words, it doesn't matter how you get there. All that matters is where you started and then where you ended up. So for example, your grade. Your grade is a state property. You know, it doesn't matter if you made a 35 on that first test, or if you made an 80 on the first test, or you made 100 on the first test. All that matters is where you end up at the end. If you can somehow get 80% of the points somehow, some way, you get a B. That's the way it is. It doesn't matter what you made on the first test versus the fourth test. If it all averages up to 80, that's a B. All right? And so that's a state property. The distance from here to Dallas, would that be a state property? Well, no, because that's path dependent. You know, maybe I get out here on I-20 and decide to drive down I-20 and maybe just go on I-20, you know, all the way there, get into South Dallas and then drive north or something like that. Or maybe I want to take the scenic route. You know, maybe I decide I think I want to go to Austin, so I'm gonna drive down to San Angelo, and then I'm gonna kind of cut across, and I'm gonna kind of make my way over, you know, on I-10, maybe go to San Antonio. That'd be fun. And then maybe drive up through Waco and then come up to Dallas that way, right? Both are ways I can get to Dallas, but are they the same distance? No, because that is a path-dependent property, the distance from here to there. All right? State properties are really nifty because they're very simple to measure. Since it doesn't matter what happens in between, all that matters is where you started and where you ended up, all you have to do is take two measurements. You take an initial measurement, you take a final measurement, and that's all you really need. You don't need to take a bunch of measurements in between like you would in a path-dependent property. Okay? All of this will make sense as we go. All right. Third concept you need to know. Here's something called the basic equation for heat flow. You'll use this quite a bit here. Q is equal to C times M times delta T. Okay. So what is Q? Well, Q is the amount of heat flowing into the system or out of the system. All right, sign convention wise, if heat is flowing into the system, it has more heat after than what it did before, so Q is positive. All right, if the system itself is losing heat, if heat is flowing out of the system, now it has less heat than what it had before, and so we say Q is negative. So Q is negative, losing heat. Q is positive, gaining heat. All right. The amount of heat a substance gains or loses depends on three things, according to this equation. The first thing it depends on is the specific heat, which is C in this case. That's what that little C means. Specific heat is a measure of how much heat a substance can absorb without its temperature going up very much. So, hypothetically, let's say I've got a copper wire. I'm dealing with a lot of copper today. And maybe I put it in the Bunsen burner flame for 30 seconds. And then I take it out of the Bunsen burner flame and I grab it with my hand. What's going to happen to my hand? Well, I'm going to burn my hand. Why? Well, because copper has a very low specific heat. You don't have to add a lot of heat to copper to get it to heat up very quickly. And so I put it in that flame for 30 seconds. Yeah, it's going to get really hot. And if I grab it, I'm going to burn my hand. All right. Well, let's say I have a beaker of water, big beaker of water, and I stick it on the hot plate. And I stick it on the hot plate for 30 seconds. And then I plunge my hand into the water. Am I going to burn my hand? Well, actually, probably not. Why? Well, because water has an extremely high specific heat, especially for its molar mass, very high specific heat. It takes a lot of heat. You have to add a lot of heat to water to get the temperature to go up. So when you put a beaker of water on the hot plate, does it start boiling right away? Well, no, it takes forever for it to boil. And the reason why is because you've got to add a lot of heat to get that temperature to go up. So if I put my hand in the water after 30 seconds on a hot plate, yeah, I'm probably going to be okay. All right. Now, if it takes a lot of heat for it to heat up, then that means it has to lose a lot of heat for it to cool down. So if I take a beaker of boiling water and I take it off the hot plate and set it over here to the side and wait 30 seconds and then plunge my hand in there, what's going to happen? Well, pretty bad things. I'm going to burn myself pretty bad because it takes a lot of time for water to heat up, but it also has to lose a lot of heat for it to cool down temperature-wise. The copper wire, I can take that out of the flame, set it on the desk for about 30 seconds or so. I can probably pick it up because it doesn't take much heat for the temperature to go up, but it also doesn't have to lose a lot of heat for the temperature to go down. Water has an abnormally high specific heat, extremely high specific heat, which is actually a good thing. The Earth's surface is mostly what? Well, it's mostly water. It's about 2/3 water actually instead of land. When the sun's shining, it's nice and warm, right? What about when the sun is behind the Earth? What if it's not shining? How come you don't freeze to death? Well, because the Earth itself holds some heat, it has a certain specific heat, but you've got all that water. And all that water starts radiating that heat off, and it cools off as it's cooling off. And by the time it cools off a little, the sun comes back out and it warms back up again. So, places that are surrounded by water a lot, like Hawaii, it's like 72 degrees during the summer and 72 degrees during the winter, and temperature doesn't go up very much or down at night. Places that are landlocked, they have no water. There's no water there to moderate the temperature. So those places tend to get really, really hot. They tend to get really, really cold. But yeah, there's a temperature swing, maybe 40 degrees, we'll say, from day to night here on Earth. Whereas it's maybe 300 degrees on the surface of the moon. There's no water, there's no atmosphere. The atmosphere probably has something to do with it as well, to help hold that heat in. Each particular substance has its own specific heat. All right. I do not expect you to memorize all the specific heats of everything out there. I would give it to you, unless, I could do this. I could say, okay, here's how much heat was released. This is the mass of it. Here's the delta T. What's the specific heat? In which case you just, plug in these two numbers and solve for C. But no, I don't expect you to memorize chart data. That's probably asking a little much. I would probably give you those values. But each substance has its own specific heat. That's the key. All right? Okay. So we take that, we multiply that by EM. EM here is your mass, and that's going to be in grams, generally. In this case, it will be in this chapter. That's pretty self-explanatory. You don't really have to explain that one, I guess. Delta T here, that's your change in temperature. Okay? Now, anytime you see a delta, and I don't care what it's in front of, if it's a delta T, delta S, delta G, delta H, delta X, delta Y, it doesn't matter. Anytime you see a delta, the way you calculate that is you take your final and you subtract off your initial. It's always final minus initial. So delta T is my final temperature here minus my initial temperature. That can be positive or negative. If my temperature goes up, it's going to be positive. If my temperature goes down, it's going to be negative. All right, but that's what goes right here. Okay, and this is the basic equation for heat flow. All right, well, let's see if we understand this. Suppose 652 joules of heat is added to 15.0 grams of water. The specific heat of water here is 4.18 joules per gram degree Celsius. In other words, I have to add 4.18 joules of heat to raise 1 gram of water from, say, 24 degrees Celsius up to 25 degrees Celsius. Okay, and we'll say it's originally at 20 degrees Celsius. Okay, about room temperature. What's the final temperature? Okay, well, we got one equation here, so I guess that's the one we're going to use. So I got Q is equal to C times M times delta T. So we added 652 joules of heat, so that's positive here, positive 652, times, here's the specific heat of water, times 15.0, that's my grams, times delta T. So we just solve for delta T. So to solve for delta T, we divide both sides by 4.18 times 15. So we run through the calculator and you get positive 10.4 degrees Celsius. Okay, what does the positive 10 mean? That means the temperature went what? Well, it went up, which makes sense. If you're going to add heat to something, is the temperature going to go up or is it going to go down? Well, it's going to go up. Okay, yeah. Okay, so at least it makes sense. So if I want to know the final temperature, how do I get that? Well, wouldn't that just be the initial temperature plus how much ever it changed? So T2, my final, is equal to whatever my original is plus my change. So if it was 20 and it went up by 10.4, my final temperature here will be 30.4 degrees Celsius. Make sense? All right, again, notice that if Q is positive, then that means the system is absorbing heat. It's taking in heat. If the system's taking in heat, that makes the molecules move faster, so therefore my temperature is going to increase. If Q is negative, then that means the system is giving off heat. That means the molecules have less energy, they're going to slow down, and so therefore my temperature decreases. You know, heat content is a measurement of energy. Temperature is a measure of average molecular motion. So they're not the same, but they correlate. You know, if you add heat, the temperature goes up. If you take away heat, it goes down. All right? Simple enough. Easier than chapter 4, right? Okay. Well, for a reaction at constant pressure and temperature, okay, think about this. Is that a situation you run into very often? Constant pressure and temperature? Yeah, quite a bit. You know, if you think about it. I mean, anything you do out on the lab bench is going to be constant pressure and temperature. You know, what's your temperature? Well, whatever the temperature of the lab is, it doesn't change very much when you're in there. What's the pressure? Well, it's atmospheric pressure, whatever the pressure in the lab is, you know, and that's going to be pretty much constant unless we're in the middle of a hurricane or something like that. So yeah, that's anything that happens out in the open air, that's a constant pressure and temperature type reaction. All right. When you have heat being given off at a constant pressure situation, which is what we've got right here, that's equal to a special thermodynamic function called delta H. Okay, and that's called the enthalpy. So delta H is the amount of heat given off. Q is the amount of heat given off. Okay, but delta H is a special Q. It's the amount of heat given off at constant pressure, which is a very common situation. Okay, so you can kind of think of them in both as the amount of heat either taken in or given off. All right, when delta H is positive, then we say that's an endothermic reaction. Okay, that is a reaction that absorbs heat. All right, there are very few examples of endothermic reactions that I can give you that you have seen, or at least are evident to you. And there's a reason why, and we'll talk about it next semester. But there actually is a reason why that is true. Probably the most common situation that maybe you have run into would be one of those cold packs. You know, not the ones you stick in the freezer or anything like that, but the ones that you take and you squeeze and all of a sudden they get real cold. You ever seen those before? All right, well, story time. You can fast forward through this if you really want to, I guess. But a long time ago, back when my son was like about 5 or something like that, we went on this little trip, and it was a Indian guide, which is kind of a less politically correct version of the Boy Scouts, essentially. And so they had these little tribes, and we had a friend, and he said, "Hey, I want to go to Fort Davis. You know, my son's in this Indian guide thing." And so I thought, hey, you know, free trip to Fort Davis, sure, why not? We'll tag along. So, you know, we got in his camper and we went down there, and it was fun. We enjoyed it. And so we got out there, and you know, there were other little tribes because it was a big giant powwow told you it's kind of politically incorrect. Big giant powwow out there of all these little tribes running around and howling. And so basically what we did is we kind of sat around the campfire, and we just kind of sent them out in the woods to go play, because we're guys and that's what we do. You know. By the way, ladies, if you ask us to watch your kids, you know, what we consider watching your kids and what you consider is a little different. You know, you probably think we're going to set them down in front of the TV and read to them and, you know, do a puzzle or something like that. No, we're going to send them outside. We're going to watch TV, and if they have an issue, they can come in and talk to us. That's just kind of what we do. Sorry. So the kids are running around all over the place, and, you know, doing whatever little boys do. And so you got little boys out there, and you've got rocks. So you guys know this. What happens when you get a group of boys together and rocks? Yeah, rock fight. Okay. So essentially they were having a rock fight with the other little tribe out there. And what happens in a rock fight? How does a rock fight always end? One kid always gets hit and starts crying. That's always the way they end, every single time. And you know what? It's always the same kid, every single time. You know, if you were that kid back in school, I'm sorry, but it's just always the same kid. So, you know, we're sitting around the campfire, and here come the kids, and they're just, this kid is just, you know, got hit in the head, and he's just screaming his head off, you know, just, and we're just absolutely terrified. Because honestly, we don't want to face the mother. You know, we would much rather talk to the father than the mother. You know, guys don't want to deal with angry mothers. It's a bad situation. You don't want to deal with that. So, you know, we're trying to patch you. We're trying to go, okay, calm down, kid, calm down. You know, rub some dirt on it. You're gonna be okay. You're gonna be okay. So we're, you know, trying to find the first aid kit. There is a point to this, by the way. And so we find this little cold pack thing in there, and I'm just sitting there thinking, I wonder how this cold pack works, because I'm the kind of guy I am, I guess. Kids bleeding over here, and I'm interested in the cold pack. So, you know, I started looking at it, and basically this is how a cold pack works. Really, all that's in a cold pack is you have a bag, and you have ammonium nitrate here, which is a solid. Does anybody know what else we use ammonium nitrate for? Well, we use it for fertilizer. Yeah, it's just fertilizer, basically. That's what it is. Okay, and then you got a bag of water. All right, and so when you twist the little cold pack, what happens is you break a seal. The water gets in with the ammonium nitrate. All ammonium salts, all nitrate salts are soluble. You know this from your solubility rules back in chapter 4. Hopefully you've looked at those by now. So it's soluble. And so as it goes into solution, this is actually an endothermic reaction. It actually takes in heat. So it takes heat in as the ammonium nitrate is dissolving. Okay? So if my system is the ammonium nitrate dissolving, it has to take the heat. It's taking heat in. Well, it's got to take in heat from somewhere. Where is it going to take it from? Well, it's going to take it from the surroundings. So what are the surroundings? Well, the surroundings would be your hand or your head or whatever you're putting the cold pack on. And that's why it feels cold. It's taking the heat from your skin, using that, dissolving the ammonium nitrate, and therefore your skin has less heat than what it had before, and it feels cold. And that's how it works. It's really that simple. So yeah, that's another use for fertilizer right there, is you could actually make a medical device. You could actually make these cold packs here. And that's probably, I would think, the most common one that you probably would have run into would be that one. But that's a good example of an endothermic reaction. Okay, exothermic reactions. I can give you tons of examples of exothermic reactions. These are reactions that give off heat. Delta H would be negative in that case. Gasoline burning. Extremely exothermic reaction. Believe me, go drive your car around, open the hood, put your hand on the engine. No, don't do that. You'll burn yourself, because that reaction gives off a ton of heat. So much heat that you have to have a water-cooled system there to keep your engine from kind of melting down to a big pile of goo or something like that. So yeah, that's a great example of an exothermic reaction. Those little hand warmers, if you want to go back into the camping examples there, those little hand warmers, little iron. Usually it's iron oxide. That's what it is, iron. So yeah, you just kind of squeeze them and twist them and this and that, and they get really warm. And you stick them in your sleeping bag and keep you from freezing. There. Used those in Yellowstone actually last year. We thought we were good down to about 45 degrees. That's what our equipment was, because it was like in the middle of summer. Well, it was like 32. My wife still complains about that. It was a good trip though. We enjoyed it. But yeah, it was cold. So we just shoved those little hand warmer things down in our sleeping bag, and we made it, through the night. But wow, you wouldn't have thought in July it would be that cold up there, but I guess it is. But yeah, that's an example. So your aluminum foil dissolving in your potassium hydroxide, that's a great example of an exothermic reaction. It gives off heat. All right, and like I say, there's more of those than there are of the endothermic, and there is a reason why. We'll talk about it next semester. Trust me, we're going to come back to this. We'll talk about it in a little bit more detail. All right, but delta H is positive, endothermic reaction absorbs heat. Delta H is negative, exothermic, exit, going out, heat going out, reaction gives off heat. Make sense? Kind of a short video, I guess, with the first one, but I think that's a really good place to stop. Next time what we'll do is we'll start talking about calorimetry, so thought maybe it would be best if we just talked about all that in one particular video. So we'll quit there for now. We'll start talking about calorimetry, which is a way to measure how much heat's given off in a chemical reaction, and I guess we'll move on from there. So I guess we'll see you in video number 2. So bye for now.